So I very much do not want to compete with Robin's lecture, which really was a brilliant description of, I mean, I wish, you've heard a good lecture about your own work when you don't understand it. It was brilliant, and I'm not going to try to compete. But fortunately for me, there is a little bit more that one can say, and this little bit more involves a sort of degenerate situation, which is not without interest in its own right, and has the wonderful property that I don't know what the answer is. I don't know even what to conjecture. But I want to describe the setup, and then maybe somebody will know what one should conjecture. So I begin by sort of a little bit repeating things that Robin said. So I want to talk about Biextensions. And unlike Robin, I'm not going to have to do much geometry, so I can describe this kind of abstractly. Let's let P be a smooth projective variety over C, just to fix ideas. I mean, it's sort of the background where all the noise happens. So we want to understand what a Biextension is. So what's a Biextension? Well, I'll just repeat what was said in the last lecture. B is a mixed height structure on P in this case. Where W minus 2 of B is, well, it's just a mixed height structure. I shouldn't say on P. W minus 2 of B is Z of 1. And ger W minus 1 of B is H, which is a pure hard structure. Wait, minus 1. And we always think in our heads of H equals H 2R minus 1 of P with coefficients in Z of R. So that's a quintessential weight minus 1 Hodge structure that we have hanging around. So I emphasize, I confused myself a minute ago. So let me emphasize for you. Here I mean a mixed Hodge structure, not a family. I'm not talking about a family. I'm just talking about one mixed Hodge structure. Right. And so Z of 1. Oh, and something's missing here. I need to know W 0 of B is just Z0. Okay. So that's the setup. But the first thing I want to do, I want to sort of focus on the case, which is the degenerate case. And that's the case when H, which is W ger W minus 1 of B, is 0. Well, I mean, that kills it, right? I mean, that's the whole interest. Actually, not quite. And so let me remind you of an example. I'll give the example in a slightly different way, and then I'll explain why it's an example. Suppose I look at H1 of the projective line minus, well, let's project this line minus, well, I'll put it this way. this is sort of abusive notation, but let me write it. S1 minus S2 relative to S3 minus S4, Z of 1. And let me actually take a minute to discuss this because it's kind of important in what follows. So if I write, let's say, capital S for the set S1 comma S2 comma S2, and so let's say T equals the set S3 comma S4, then what I can, this, as I've written it, doesn't make any sense. Right? What does it mean to put that sign in there? But it would make sense to write H1 of P1 minus S relative to T with Z of 1 coefficients, providing that I assume that these 4 points are disjoint. I mean, that is the set S3 and S4, so capital S intersect capital T should be empty. Right? So in that situation, we can actually compute this cohomology group, and well, I mean, you know how to do it. So let me just write down a number here. I sort of, the way I've done it, it should be. I think what I've got here is S3. Somebody correct me if I've got this wrong. Minus S1. No. S3 minus S1. S4 minus S2 over S3 minus S2 and S4 minus S1. So having assumed that these two sets are disjoint, this is a finite number. So this is actually, assuming that the points are distinct, this is NC star. Right? So that, of course, was known to the ancients, and that's the so-called cross ratio. Of the four points. Okay. So what I want to talk about in this lecture is a kind of a generalized. So I want to talk about a generalized. The generalized cross ratio, which will have a similar construction, but we'll be dealing with higher dimensional cycles. And it will take values, just as this one did, take values in C cross. Okay. So, but before I start doing geometry, let's just take a minute to try to understand the setup in terms of Hodge structures, right? We said that the GER minus 1 should be 0. I hope I said it somewhere. That's the key condition here, right? And so therefore the Hodge structure, this B, in our case is just a stupid looking thing. It looks like this. It's 0 goes to Z of 1, goes to some middle term, goes to Z of 0, goes to 0. Well, actually, so the first thing that a modern mathematician would do, looking at sets, and say, well, you know, what can we say about M? How many different M's are? And so, in other words, we'd like to look at the X group in the category of mixed Hodge structures of Z of 0, Z of 1. Okay. Well, so what is that group? Well, it's not actually trivial. I mean, it's not hard now. We know the answer. The answer is it's a multiplicative group. It's C cross. But it was, in the day, it was an interesting question. And it was solved by Carlson. And it's kind of an amusing, I actually don't know the details of the story, but the outcome was that his manuscript was lost. That it was published in a journal that either went out of business or kind of lost the will to continue, or I don't know. But in any case, for years, the result was folklore, and even the reference existed, but nobody could access it. It wasn't really it was vaporware. And it was only by the work of various people. I actually got this from a manuscript which is on the web, notes by Chinese mathematicians. Min, what was his name? Ming Chen Xia. And the title of the notes are Notes on Hodge Theory. Carlson's correspondence. So let me describe following, well, I won't give the full details, but let me follow Min Chen Xia's description of the actual proof of that assertion. It's not totally trivial. So the general result is the following: X1, the category of mixed Hodge structures, of W and V. So here, let me assume W and V are pure Hodge structures. I don't need anything more than that. And the result of Carlson is that this is isomorphic to the points of the Jacobian of the Hodge structure, which is Hom Z of W. So here the Jacobian of a Hodge structure. So what's the Jacobian of a Hodge structure? Well, let's say Hodge structure X is, by definition, it's the zero weight part of the complex points of X divided by the zero weight parts of the rational or integral, not X, oh, yeah, X, plus F0 of XC intersect W0 of XC. So that's, and this is a definition. Okay. So just I don't want to go take too much time on this, but just to give you a flavor of how it works, we construct a map X1 W V into this J of Hom So let's, if we have an element in X1, right? So that's 0 goes to V, goes to E, goes to W, goes to 0. So that's in there. This is in Hodge structures. Then, if I call this map pi, then what we do is we cook up maps backwards, like that and like that. So call this one R, this one S. So R is a map. So R takes E to V, is supposed to be a map of filtered Z. So it's R filtered Z modules. So we have the weight filtration, so it gives me a filter structure, and this is taken to be such a thing. And S, so there's a map from W C to E C, if I got this right, is a section, and this is more subtle, section of pi, which is a morphism, of C mixed Hodge structures. Did I get that right? Morphism of C mixed Hodge structures. Yes. And I'm not going to get into this, but it's more subtle, the existence of such an S. It involves a rather deep and tricky formulation of Deligne for the notion of, well, for certain notions in Hodge structure. So I'm going to dodge that. But in any case, assuming that we have an R and an S, then, so assuming given R S, then we can compose and take E, which is an element in Hom C of WC VC. E equals R composed with S. R, the other way, R, yeah, no, that's right. First do S and then do R. And we find that E, I hope the assumptions here, so let's see quite why this is true. E, so E is R composed with S, and E is, for some reason that escapes me, but it's true, E is in W0 of Hom C W. Okay. Then, recalling this X1 of W V is equal to W naught of VC modulo W naught of W naught of VC modulo W naught of Z, I suppose I should say here, Vz, or VQ or something. Just doing more of V plus F naught of VC plus, yeah, sorry, this is, forget this. F naught of VC plus W naught of VC. There should be intersection. Sorry, I've written this wrong. It should be intersection. Sorry. F naught should be an this should be an intersection. Right. Yeah, this is an intersection. Right. Okay. So anyway, that's the construction of the extension map here. So the example that I want to focus on, I mean, I don't really care about the general result. It's a nice result and it's true. But I want to focus on a very simple case that I mentioned earlier, just the extensions of Z by Z of 1. Okay, so the application is that X1 mixed Hodge structure, Z of 0, Z of 1 is, well, it's W naught, so you have to reconstruct the Jacobian, and if I don't err, what you get is W naught C of 1 factored out by W naught Z of 1 plus F naught C of 1 intersect W naught of C. Okay. And what that is, I mean, you have to think about, so Z of 1 has weight minus 2 and has Hodge degree minus 1. Right? So F naught C of 1 is 0. Because it's smaller than the Hodge degree. The Hodge filtration gets smaller as the index increases. So this is 0, and a W naught Z of 1. Well, Z of 1 has W minus 2 is non-trivial. So W naught Z of 1 is just Z of 1. Right? So in fact, what we get here, and by the same token, W naught C of 1 is C of 1. So this is equal to W naught C of 1 divided by W naught Z of 1. And that's equal to just C of 1 mod Z of 1. But you have to think for half an hour or so, you convince yourself that what is C of 1, right? It's just C, right? The filtration, the weight filtration, the Hodge filtration, which is controlled by the index here, is trivial on the C on a C Hodge structure. So this is the same as just C, as a abelian group. This is the same as C mod Z of 1. But C mod Z of 1 by the exponential is just C cross. So something tricky has happened here. I've gone from the category of Hodge structures to the category of abelian groups. But you have to get used to that. I will do that several times in the course of the lecture. Okay, so this is nothing. It's nothing Well, it was something for Carlson to work this out, but in today's world, it's easy. Okay, so now what we'd like to do is construct extensions of z by z of 1. Because if you recall, the lecture began, and the last lecture was involved with extensions, which are not extensions, but mixed Hodge structures, which were examples of Biextensions. And we want to study in this lecture degenerate Biextensions, which are literally just elements in here. So we want to get elements in there, and we now see that we can, and they are parameterized by C cross. Well, so here's how you might imagine it works. Okay, so that's an exact sequence of abelian groups, topological groups, or whatever. So I can put the same, maybe I should call this Z1, because there's a 2 pi I. So here I'll write down a similar situation, but this will be Hodge structures. So here I'll put a question mark, because we're looking for an extension, and here I'll put Z of 0, which has as its Z structure just Z. So here on the Z structure, I can give myself a map which sends 1 to some element, call it A, in here. Right? So now what you can do is take the fiber product. So you can call, let's define M sub A to be the fiber product, C fiber over C cross, with Z of 0. And then we find, indeed, that 0 goes to Z of 1. M A fits into this MA, fits into this sequence. This is 0. The only drawback is I haven't really given you a Hodge structure on this MA. This is all just fantasy, right? And in fact, I don't really know how to give you a Hodge structure from this point of view on this thing, but it is certainly the case that this is I didn't give the full proof, but the theorem of Carlson says that there is a fellow in here that has a Hodge structure that makes this bottom line be an exact sequence of Hodge structures. So I just raised this as a question, is can we give MA a Hodge structure in such a way that this is exact? And that's sort of phrased negatively because it's a question, but we know by Carlson that there exists, call it, let's say, an M A prime, which fits into the exact sequence to 0, 0, and makes that a sequence of Hodge structures. Okay, now why do we care? So where are we so far? We've established that if we work with these degenerate Biextensions, which have 0 term in middle degree, then we are led to, sorry, guess we don't have an eraser here. We are led to extensions of Z by Z of 1, and we know by Carlson's theorem that they exist. And my pathetic attempt to construct one didn't work, so we fall back on Carlson's theorem. It says they exist. Okay. So what are we going to do with this? Well, let me remind you of the classical Biextensions. So what do I want to? No, sorry, I don't want to talk about Biextensions. I want to talk about cross ratios. And in fact, I want to talk about the classical cross ratio, which is an invariant associated to 4 distinct points in P1. And in fact, we can be a little bit more precise. We'll write it down here. Yeah, so if we take S1, S2, S3, S4, and P1, distinct P1C, let's say, distinct, in fact, P1, no, distinct points, then the cross ratio is, well, at least my version of the cross ratio, I mean, there's some choices here. I don't know if I necessarily made the right ones. S4. See, it's not 0 if they are distinct points. So it's not equal to 0 infinity. And it's an element. Okay? So what am I after? Why am I telling you all this nonsense, which you probably already know anyway? I want to claim that this cross ratio, well, first of all, we see, which maybe was not familiar to everyone, that this cross ratio is naturally associated to a degenerate Biextension. That is, to a Biextension who's vanishing with the vanishing middle term. So let's consider, on the other hand, our Biextensions. We discussed, I guess I erased it, but we discussed Biextensions on a general variety, smooth projective variety P. So P is our smooth projective variety, and let's say B is a Biextension. Biextension. Right. And suppose it's degenerate. So what matter of object? So if B is degenerate, so that means that the middle term is 0. So if B is degenerate, so that says our H, which is where W minus 1 B is 0, then what is a geometric description? Of B. I mean, I've kind of set things up here. You naturally expect that it's going to have something to do with 4 tuples of rational objects on the projective line. And indeed, it does. So how do I explain that to you? Let me consider the most interesting, it's a special case, but it's the most interesting special case. So let me suppose that B is equal to H2R minus 1. I'll put a twiddle over it to indicate I'm taking, it's a little bit more elaborate than just the cohomology group itself. So I'll take P minus some subvariety y relative to another subvariety z, and with z of r coefficients. Well, that's cheating. Really, what I've described for you here is the middle term here. But we can read off, and I'm assuming my middle term is 0. But we can read off the rest of the terms. Well, in fact, we know the rest of the terms. So b of 0 is to be z of 0, and b of 2 is to be z of 1, and the middle of b 1 is to be 0. So maybe I'll put, well, the tilde here means that I'm not actually talking about a cohomology group here. I mean that B is the data that we assemble from such a list of objects. All right, now, such a list of objects will give me a Biextension. So I assume here that the support of Z intersect the support of Y should be empty. But it will not in general be the case that there's no B of 1. So I have to massage these objects, and for that it's sort of a nuisance to do it every time. So I'll just put a tilde here. So the tilde here indicates that Y, I think of Y not as a single object, but as a difference, y1 minus y2. So I think of it as a cycle of degree 0, which is a difference of two physical cycles, y1 and y2. And by the same token, I think of Z as being Z1 minus Z2. So Y is a cycle homologous. What's important to me is it should be homologically equivalent to 0, and it should be of whatever degree of codimension R. And Z should be a cycle homologically equivalent to 0, and it should be of dimension R minus 1. Okay. So, for example, if I was talking about a curve, so if P was a curve, then Y should be codimension 1, Y should be some points, so R should be 1, and R minus 1 should be 0, so these should be both 0 cycles. So these are points. Notice here we're talking about codimension R, and here we're talking about dimension R minus 1. So they're the same. And in fact, if we're talking about Y codimension R and P of dimension 2R minus 1, then we're going to get the same kind of picture. We're going to get codimension R cycles here and here. So that's the geometry, but we've made this exotic assumption that the interesting middle term vanishes. Okay, so what do we get? Okay. So B is an element in X1 mixed Hodge structure of Z by Z of 1. And we just saw, we computed this. This is C cross. Okay. So that means that, well, let's consider a slightly more elaborate situation. Let's consider M in N, say, free abelian groups. say they're of the same degree. They're isomorphic to z to the, I don't know, z to the. Then we can consider a more general B in X1. Or maybe I should say B of M and N. B of R, maybe better, in X1, next Hodge structure, Z0, answer M, Z of 1, answer N, by just, I mean, we do something stupid. We just take M, Z of 0, so Z of 0, well, M, let's say M, this is that, M, R, and N, Z of S. So then I get just Z of R here and Z of S here. I mean, I'm not doing anything, but I get more copies of the set. So I get more copies of that. So what do I get? I get a map from, I claim that this gives me a map from Hom M N, just as free abelian groups, into C cross. Right? Because if I have an extension like this, and I've given myself this B, which is an extension like this, then for each element in a basis here, and of course, and an element in a basis here, I'll get an extension, and so I'll get an element in C cross, which would be the extension class. I'm sorry I didn't explain that very well, but if you think about it, it's clear that I get, and this, of course, is just Z to the M is rank R, and so ZR S, I suppose M is rank S. So I get a map from ZRS to C cross, right? Okay, so where are we? What I want to claim is that this is an interesting way to get a generalized cross ratio, right? So these elements, this is a map. Let's call this rho, and it depends upon the B. Rho B gives me such a map, and this is a generalized cross ratio. Now, I'm sorry it hasn't been very, very coherent, my explanation, but I want to claim that nobody's ever looked at these things. I don't know anywhere in the literature where one considers systematically such maps. I mean, I probably, no, here it is right there. These maps generalize the cross ratio here, but it's an extremely general situation that arises whenever I have extensions of Z by Z of 1. Let's see what I want to say here. Yeah, so let's consider slightly more precisely here. Suppose, for example, H2R minus 1 of my P, and Z coefficients, is 0, right? Which is certainly the case for the projective line. Right? Then the conditions are fulfilled whenever we have y and z contained in, what did I call in P? Y codimension. Y codimension R and Z dimension R minus 1, as above, we will always get, so this will yield an element give the element the name E of Y and Z in C cross. And if we take a collection of these, then we get a collection, so we get an element in C cross to some power. Okay. This is what I mean by a generalized Biextension. Generalized Biextension. And the question arises, what are these things? Right? You don't find in mathematics sort of natural collections, natural rational numbers arising from geometry without some kind of meaning. Right? So they are associated to algebraic cycles, which is why I like them, because I like algebraic cycles. So we get numbers associated to algebraic cycles. And just by way of example, I have a little more time. Just by way of example, the kind of, when I say, what do these things mean? There's been a lot of work recently on functional equations for polylogarithms. And my sense is that, I mean, the one that's known in the case of a 4 logarithm is that if we have 5 elements, so it's A1 up to A5 in C cross, and then we just simply take the sum, minus 1 to the I of the 4 tuples, A1, AI, leave out A5, and that sum gives 0 in a certain complex. I leave you to pursue that in the literature, in a complex in the polylog, complex of Goncharov. And now this is exactly a machine for generating similar type situations, but I don't want to claim that I know of complexes where these things give relations. The point being that A1, A4 is associated with the cross ratio. Right. So I could say more, but I think that's kind of enough. Yeah, I think that's kind of enough. There's in general, one should think of these points not as being in C star, but as being points of a torus, depending upon the torus, the dimension of the torus, depending upon the situation. And you can formulate a more general setup in those terms. But I think this is enough to give an idea. Okay.
Thank you. Some questions?
Is there any example of you house rather than one?
Another example. Yeah, I mean, this is a good question. You could take P3 and take 4 tuples of lines. I'm not sure that clarifies. I mean, I wouldn't know. Yeah, if I did that, I could do that, but I wouldn't know what this is. You see, I mean, there's a little more mystery here. It seems so simple, but there's a little more mystery than you might expect, because the cross ratio itself, what is it? So, okay.
Some questions or answer, what is it? So if it's not the case, we answer.